Hello and welcome back to this course. So last class we were looking at the characteristic curve of a fuel cell that involves hydrogen and oxygen as a reactant species, water as an output species. So this characteristic curve, which is also called as current voltage curve, we can also call this as a performance curve. Let me write it down. We can also call it this as performance curve. So we started understanding how this curve comes, and so we started with the enthalpy of the reaction, and which is the maximum energy content, which is 286 kilojoules or 286 kilojoules per mole on intrinsic basis. And if you try to convert this enthalpy, which is minus 286 kilojoules, to corresponding potential, and how do we do that? We can divide any energy, as we can see it here, any energy by NF, we can convert that energy into respective potential. There should be minus here. So once we can convert all these energies into respective potentials. So if we try to convert the enthalpy, which is minus 286, that corresponds to potential called as thermoneutral potential, which is equal to 1.48 volt. So ETN, as I can write it here, ETN is thermoneutral potential. The reason why it is called as thermoneutral potential, because we are directly converting the enthalpy, which is maximum energy content, into the corresponding potential. We are not bringing any thermodynamics here while we convert the energy into the potential. So that is why it is called as thermoneutral potential. It is denoted by E superscript Tn. Moving further, so once the cell is, let's say it is operating at standard temperature and pressure conditions, so there is a loss due to entropy. So that, in other words, the energy that is lost to the surroundings, and that is basically covered by this entropy loss. So the energy that we have with us is basically Gibbs free energy. Let me write it here. This is delta H naught and this is delta G naught. So this is the Gibbs free energy, which is, if we convert into corresponding potential, we can get close to 1.23 volts. So this E naught, as we have already discussed many times, that E naught is nothing but reversible cell potential at standard temperature and pressure conditions. So this is denoted by E naught. However, all the cells that we come across, whether it's a fuel cell or electrolyzer, or fuel cell in this case, they are all operated at different temperatures and pressure conditions. For example, we saw in the numerical that the given cell was supposed to operate at 80 degrees Celsius and 3 atmospheres and 5 atmospheres of pressures for hydrogen and oxygen respectively. So this deviation also leads to a further loss, which is denoted by deviation from standard temperature and pressure conditions, and the corresponding potential is calculated, or it can be calculated through Nernst equation, and which is denoted by E superscript capital N, which we have already gone through. We have already come across this En. Moving further, we have in some cases some loss due to fuel crossover, as I was explaining in the last session, that when we have, let's say, electrolyte and then electrodes, that is anode and cathode, and once we supply hydrogen and oxygen to the cell, instead of hydrogen getting oxidized to protons and electrons, this hydrogen gas directly or in through small pores reaches the cathode and gets oxidized at cathode instead of getting oxidized at anode. So this is highly unfavorable, because we are losing fuel, that is hydrogen, to cathode side, and which is highly not recommended. And this loss is basically arising due to the fuel that is crossing the electrolyte, that is crossing or rather moving from anode to cathode. So that is why this loss is called as loss due to fuel crossover. It's a negligible loss, and it depends, or rather its magnitude depends a lot on what is the thickness of this electrolyte, and this we will discuss even more when we discuss the ohmic losses. So finally, if we have a fuel cell, we will be able to see the potential across the terminals, which we call it as open circuit potential or open circuit voltage, which is abbreviated as OCV, and this is the potential that we can see that is actually available for us to which we can explore to basically when we draw more and more current. So, theoretically what we expect is, as long as I draw more current, the potential should remain constant, and theoretically we should get the voltage performance like this. At OCV we expect potential to remain constant no matter what current we draw. So, this is a very ambitious or rather highly ideal case. In practice it does not happen, and how we get the characteristic curve is, I have shown it already. It typically goes like this, and why this potential follows this path is again characterized by what materials are used or what materials we used in a fuel cell to basically when we assemble the cell. So, the first loss or first drop in the cell performance in terms of potential is called as activation zone, as I have already written here, activation zone. And here out of these three losses, the first loss dominates, which is called as activation loss. This is denoted by eta activation. And moving further, when the potential linearly varies with the current, so that is your second zone, which is called as ohmic zone. And why it is called as ohmic zone? Because the potential is most proportional to the current that you are drawing. So, it is this zone has got a linear trend with respect to potential and the current, and that is why it is called as ohmic zone. And the loss that dominates in the second zone out of these three is the ohmic loss, which is denoted by eta ohmic. And as and when we still go ahead and draw more current, we can see that there is a sudden drop in the potential. This is happening, or this happens because of the mass transfer zone or the mass transfer loss, and this is denoted by eta mt, or we can also write as mass transfer loss. So, these three losses play a huge role, and these are the losses that determine how the performance of this fuel cell or any fuel cell of interest would look like. So, the efforts are, as I discussed earlier, efforts are basically to minimize these three losses so that this current voltage curve remains as horizontal as possible with respect to the line that I have drawn here. So, efforts are basically to make this probably like this or even like this. It should go as high as possible so that the losses that are incurred in the cell get minimized. So, let me rub this up. Okay. So, if I try to redraw this fuel cell curve, so this is, let us say, open circuit voltage, which is around, let us say, 1 volt. This is my potential axis, this is current, so it goes like this, and this is the loss. So, basically, so with respect to the energy that we have, this is your eta activation, this is the, as you go even further you have few more losses coming into picture. So, this is also eta activation plus eta ohmic plus eta mass transfer, out of which in the second case the ohmic zone dominates, and it does not mean that the other two losses are not present there. In the second zone we have both of these losses are present, that is activation loss as well as mass transfer loss are also present, but only the second one, that is ohmic loss, dominates here. In the first case even the other two losses are also present plus eta mass transfer. However, the first loss, that is activation loss, dominates, and coming to third case, again we have these three losses, eta activation plus eta ohmic plus eta mass transfer. Again we have all those losses coming up. So, the last loss, that is mass transfer loss, dominates in the third case, and that is one of the reasons why we have a sudden drop in the potential. So, let me write what this activation loss means. So, activation loss, it is basically denoted by eta activation, and it is basically the energy required to kickstart the reaction at respective electrodes. So, when we talk about hydrogen oxidation on the anode side and oxygen reduction reaction on the cathode side, we need to invest the energy to basically start these reactions at the respective electrodes, and that energy which is drawn from the very source itself is basically nothing but the activation energy which we have to invest, and that is why it is a loss to us, and that is why it is called as activation loss. Second is your ohmic loss, denoted by eta ohmic. So, this is basically, it is the loss due to the inherent resistance offered by different materials So, typically as we can see, ohmic loss takes into account two major losses. One is, let me write it, the resistance offered to the ions that flow in the that flow across the electrolyte. So, it is basically electrolyte resistance, Second is the resistance offered to electrons. So, this is basically electrical resistance. So, basically ohmic loss deals with all the charge species, and charge species is basically the ions. In hydrogen oxygen fuel cell, let us say we have a polymer based fuel cell. So, this is hydrogen and this is your H plus, and this is the electrons that flow across the or through the external circuit. So, these are our charge species, H plus and electrons. So, depending on the type of fuel cell, you can expect either protons, or that is H plus ions, or OH minus ions, or the other type of ions, or the cation or anion. So, those species, when they travel through electrolyte, what is the resistance offered to them? So, that is basically covered in the ohmic loss as the charge species, one of the charge species. Second one is the electron when they travel through the external circuit, or when they travel through different components of the cell, when they jump from one material to the other, there is also a resistance offered to those electrons, and that is also incurred in this ohmic loss. Third is your mass transfer loss. This is also called as concentration loss. It is denoted by eta mass transfer, or we can also write eta concentration loss. So, as we can see, this mass transfer loss typically arises in the third, or when we are drawing a large amount of current from the cell. So, it gets dominated particularly in the high current zone. So, let me write this up. So, as the current drawn from the fuel cell increases, the fuel that is hydrogen, or we can also think about the oxidant, that is oxygen on the cathode side, the fuel at, or I can write fuel or oxidant at respective electrodes. Basically, we have this fuel or oxidant does not reach properly, and that further leads to fuel cell starvation. So, basically when we are drawing more and more current, what happens is at the, let us take an example of anode, wherein we are supplying hydrogen at a fixed rate and or fixed, let us say, flow rate. So, what happens when you are drawing more current, more and more fuel which is reaching at this electrode and electrolyte interface, that is getting converted into protons and electrons. So, when I write H2 gives 2H plus 2 moles of electron. So, what happens is this 2 moles of protons, they quickly get into the electrolyte and these electrons move through the external circuit. So, there is nothing left, or rather very less concentration of protons that is left at the interface of anode and electrolyte. So, this ultimately leads to drop in the potential because we have no fuel there. So, that, or the quantity of fuel at this interface is so low that the cell starves. Cell starves means it finds very low fuel at this interface. So, that is what leads to fuel cell starvation, and once this fuel cell starves, the potential drops. So, all of a sudden, and that is what we can see here, it is a sudden drop which takes place, and that is one of the reasons why fuel cell is never operated very close to mass transfer zone. So, I can explain this with more example. We are dealing with mass transfer loss itself. Or I can write this as concentration loss. So, let us take an example of bucket, okay, and there is a tap through which expect water to be supplied to this bucket, and there is one more tap that is connected at the bottom of the bucket. So, let us take an example that this tap which is supplying water to the bucket is supplying water, let us say 1 LPM, okay. So, it is 1 liter per minute, and initially there is no water. So, this is my first case. So, I am drawing no water from the bucket. So, it is 0 LPM. So, this will lead to complete filling of this bucket all the time. So, this is the case when we are drawing no current from the cell. Let us say you start drawing small amount of water from this bucket. So, let us take an example of, let us say 0.3 LPM. So, when you draw, or when you take some quantity of water from this bucket, the water level in the reservoir, this bucket will be reduced slightly. However, it will still be, have considerable quantity of water. However, if we increase this water outlet at the, which is through this tap at the bottom of the bucket, the water level will further go down, and if I start taking all the water that is being supplied to the bucket, the water level will reach the bottom. So, this is the case when I am supplying, let us say, fixed quantity of liter. In order to, let us say, overcome this problem, I again go and increase the water level or water quantity that is being supplied to this bucket, and in the second case, so this is my case number 1 and this is my second case. So, this is my case number 1, and in second case I will again repeat the same. Initially I do not draw any current, sorry, any water from the bucket. So, that way it will still maintain its level, the bucket will be full all the time. When I draw a small quantity of water from the bucket, the water level will decrease slightly, but it will still be almost completely full. As and when I draw more and more quantity of water from the bucket, the water level will start decreasing, and if I draw almost same quantity of water that I am supplying to the bucket, the water level will reach at its bottom. So, what we can imply from this is this water level, let me use the other color, this water level in the bucket can be correlated to the, this is water level, it is analogous to your cell potential of the cell, and this water that we are supplying, this is your flow of the fuel. So, this is your fuel supply, whereas the case 1 and 2 represent the amount of current that we are drawing. So, this ultimately leads or is analogous to current that we are drawing from the cell. So, as we can understand, if we draw more and more current, or sorry, more and more water from the bucket, the water level in the bucket is likely to decrease and finally is going to reach 0 or minimum level. Similarly, if we draw more and more current from the cell, we are supposed to basically lose the fuel that is to be present at the interface of electrode and the electrolyte, and that is what leads to fuel cell starvation, and ultimately that leads to the drop in the potential all of a sudden. So, this is one example that we can talk about. In case of electrolyzers, let me explain a bit about electrolyzers. So, I am not at all as of now concerned with what type of electrolyzer we are dealing with. It is any electrolyzer will have a current voltage characteristic curve. So, this is my current and this is the potential. This is exactly reverse in case of electrolysis. So, the performance curve goes something like this. So, this also has 3 regions. This is region 1, region 2 and region 3. So, this is again your activation loss dominates here. Then we have second zone where the ohmic loss dominates, and then we have third, that is concentration loss dominates here at the in the third zone. So, this is the place, or if the cell is operating at standard temperature and pressure conditions, the E naught is basically minus 1.23, or I can write 1.23 minus, as we can say, it is a symbolic and it means that we have to supply the energy. So, this is our E naught. So, it is the potential, it is the minimum potential that we have to supply in order to break the water. So, the cell potential this current voltage curve will start at 1.23 volt, and I will go eventually, or we follow this path depending upon what materials we use, what catalyst we use, what electrolyte we use, and accordingly this can be characterized. And if we are operating the electrolyzers in very in the normal practice, these electrolyzers are operated at much higher temperature and pressures. For example, this polymer electrolyte membrane based electrolyzers operate typically at 70 to 80 degrees Celsius, and the pressure is as high as 10 or 20 bar or sometimes 30 bar as well. So, these temperature and pressures make they facilitate in such a way that we get this potential, or the minimum potential that is required to break the water will be lower than 1.23 volt, and that is how the this electrolysis curve starts little lower compared to 1.23, probably at 1.1 or 1.15 or 1.2 volt. So that basically underlines the fact that if I am operating at, let's say, T equals 80 degrees Celsius, instead of starting this curve at 1.23, it probably will start at 1.15. Okay. So this is at 1.15 volt. So what does it imply? It implies that we need to supply little lower electrical energy to break the water at if 80 degrees Celsius, and that basically brings down our electrical consumption to generate these hydrogen and oxygen gases. So however, if let me just underline this energy equation one more time. So we have this enthalpy, which is equal to gives free energy plus entropy term. So if you look at, in case of electrolysis, this is 286 kilojoules, this is roughly 237 kilojoules, and this is roughly 50 kilojoules. So ultimately we have to supply 286 kilojoules of energy if you want to break the water molecule. So this is H2O giving H2 plus O2. So if you want to break this water, we have to supply 286 kilojoules of energy. It can be in the form of electrical energy. This goes as a measure of electrical energy, and this one, this is thermal energy. So what it implies is the amount of energy that is supplied to an electrolyzer depends on, basically it is a sum of two major energy sources. One is your electrical energy source and the other one is thermal energy source. So if we increase the operating temperature of your electrolyzer, or in other words, if we increase the temperature at which the water is supplied to the electrolyzer, the electrical consumption, the second portion, will come down such that the total of these two equals the 286 kilojoules. So that is one of the reasons why, if the cells are operated at much elevated temperatures, and that is the advantage that we get with respect to solid oxide electrolysis, as these cells operate at much higher temperatures, the electrical consumption comes largely, it gets lowered, and that is how we can save the electrical energy. But we need to remember the fact that we have to supply both of these energies, so that the electrical consumption of this electrolyzer gets reduced, and then we can save in terms of the cost. So with that, I thank you all. I'll stop here and I'll take on with the efficiency calculations, and with respect to fuel cell as well as electrolyzers in the next class. Thank you so much.